Okay, guys, so here we are with video 12, which is taking the derivative of the inverse trig function. And I listed those inverse trig function derivatives here for you, but I'm actually going to take a couple of moments to explain. I'm going to do 1 through 3. You could probably do 4 on your own once I show you how to do 1 through 3. I think it's good for you to know where they're derived from. No pun intended, because it's helpful if you needed to recreate it fairly easily. Also, if you are a junior and you're planning on taking like multivariable calculus next year, this is something that you will definitely use in multivariable calculus. So let's take a look. So the first one that I'm going to do is the derivative for the sine inverse. So I'm going to kind of do this the same way that I've been doing problems recently, which is I'm first going to write out what I'm going to take the derivative of. And this is in terms of u, assuming that there might be a function inside for chain rule, but I'm going to do it for x, and then so that way you can see it a little easier. So this is really sine inverse of x gives me y. So I'm going to actually do the sine of both sides. So imagine I'm taking the sine of both sides. That would give me x equals sine of y. And then in a moment, I'm going to take the derivative of this. But before I do the derivative of this, I'm going to create a relationship using a right triangle. And this may take you a couple of times of looking at to understand. So imagine that I have a right triangle. I'm going to go ahead and make my hypotenuse 1. You'll see why. Well, I can hold on off on that for a second. So if you take the sine of something, this something is the angle. So I'm going to put my little angle y here. And this is saying that the sine gives you x. Remember, the sine ratio is opposite over hypotenuse. So if I'm going to get out an x, my opposite would have to be x and my hypotenuse would have to be 1. Once again, the sine then would be opposite over hypotenuse. So this makes this true. So this is what this triangle looks like. Now, in that triangle, I'm going to need the other side of the right triangle, and I can get that other side. I won't have an actual number, but I can express it in terms of x. So for what I mean by that is like if this side is a for a moment, then a squared plus x squared has to add up to 1. That's Pythagorean theorem. And if I want to solve for that side a, I would do 1 minus x squared. And then to finish, I'd have to square root both sides. So a would be root 1 minus x squared. So I'm going to go back over here. I'm going to rewrite this side. Oops. I'm going to rewrite this side as root 1 minus x squared. Okay, now I'm going to need this triangle in a second. So let's go back to the problem. So remember, I wanted to take the derivative. I need the derivative of this. So here I go. I'm going to take the derivative. Derivative of x is 1. Derivative of sine of y is cosine of y with a dy dx attached. There's my derivative. I'm going to divide both sides by cos, and I have the derivative. But once again, we would rather not have a y on the problem. So we're going to do this last step a little differently than the previous few videos. So instead of going back and like replacing, because I actually don't have something for cos, I have something for sine, I'm going to use this triangle. Remember, the cosine of y would mean I want the adjacent side to y over the hypotenuse. So this part can get replaced with what the cosine is. So the adjacent side would be root 1 minus x squared over the hypotenuse, but the hypotenuse is just 1. So there we have it. The derivative for the sine inverse is 1 over the square root of 1 minus the function squared. And it is like this. So then in the future, if there is something in here other than just an x, you're going to have to square that and then multiply by the derivative of what's inside. So we'll do that in our examples. Okay, so that's for sine. So let's look at it for cosine, and this time you actually may be able to do some of it with me. We're going to have a slightly different triangle. So, okay. So I'm going to start with cos inverse of x equals y. I'm going to take the cosine of both sides, and then I'm going to make my triangle on this relationship, which is slightly different because this time I'm saying the cosine of y. So y is still my angle. The cosine is x, so that would have to be adjacent over hypotenuse. The only way to get out x is for the adjacent to be x and the hypotenuse to be 1. And using the same thing we did over here, if I tried to solve for this side using Pythagorean theorem, I'd get square root of 1 minus x squared again, but the 1 minus x squared is in a different spot. So keep that in mind. Okay, so now let's do the derivative. Derivative of this side is 1. Derivative of this side is negative sine y dy dx. Once again, I can divide both sides by negative sine y. And then finally, I'm going to replace what the sine of y is using this triangle. Well, sine is opposite over hypotenuse. So the opposite to y is this, over the hypotenuse is 1. So I'm going to bring that negative up over the sine. Remember, again, the sine of y was just root 1 minus x squared over 1. That's why I didn't really need the 1 on the bottom. So here you go. So there's the inverse derivative for cos. All right, last but not least, let's do it for tan, and then you can do the sec inverse if you want on your own. So same thing, I'm going to start with tan inverse of x equals y. I'm going to take the tan of both sides and re-express it, and I'm going to create a triangle. So this time, the tangent of y, which is opposite over adjacent, is x. So if I want opposite over adjacent, remember, I'm kind of treating this x like x over 1. So opposite would be x, adjacent would be 1. This time, if I want to get the hypotenuse, which I'm just going to call h, I would just take the square root of both sides, and I'd get square root of 1 plus x squared. So this time, it's a 1 plus x squared because of the Pythagorean relationship. Okay, so let's do the derivative of both sides and see what happens. So 1, oops. So I'm going to do the derivative of this now. I get 1. Derivative of tan is sec squared y dy dx. And then that's technically 1 over sec squared y. And if you really want to get creative here, sec squared on the bottom is the same as cos squared in the numerator. And then we're going to replace this with the relationship. So now I'm going to treat this as cos y and then square it. So what's the cosine of y? We'll go back to your triangle. Cosine is adjacent over hypotenuse, so 1 over root 1 plus x squared. Square that, the top would still be 1, but now the bottom loses its radical. And there you have it. Again, if you want to try that fourth one on your own, you can. I think you could probably get there on your own, but let's use some of these now. Okay, so we're going to start with the sine inverse. Let's just remind ourselves what that is. The sine inverse, once again, is 1 over square root of 1 minus x squared, or chain rule if we need to apply it. So let's go. Okay, first of all, I am going to need the chain rule here. So I'll start with my derivative, 1 over square root of 1 minus what's inside, squared, times the derivative of what's inside, 1/3. So to finish it, I would leave it as 1 over 3 root 1 minus square the top, square the bottom. The top would be x squared, the bottom would be 9. Now, if I really wanted to start putting this stuff inside together, I could. I could multiply this little guy right here by 9 over 9 so that it would have common denominators. This is actually kind of helpful. So then I have 9 minus x squared over 9. You are allowed to take the square root of the top and bottom separately. So the square root of the top would stay that way, but the square root of 9 actually does reduce to 3. So technically, at this point, I just have this guy. I already did the square root of the 9, which is the 3. These 3's would cancel, and I just get 1 over root 9 minus x squared for my derivative. Pretty nice. Okay, let's take a look at this guy. This guy is actually a product. I hope you guys noticed that. And one of the parts of the product is an inverse, and whoa, the inverse has a chain rule, a function inside. One step at a time, guys. dy dx. Here we go. Derivative of the first, 2x times the second. Cos inverse 3x. That wasn't too bad. Plus the first times the derivative of the second. So the derivative of cos is negative 1 over square root of 1 minus the function inside squared times the derivative of the function, so times 3. This guy's fine. I'm just going to go ahead and clean up what happens here on the right. So I end up with a minus 3x squared on top over root 1 minus Square both, 9x squared. And this is fine. All right, I think this is the last one. Yep. So for this one, we're doing a tan inverse, and I want the equation of the line tangent at this value. Well, that means I need the slope or the derivative, and I need it at a point. Now remember, I need the point, and I need the point to be what I get when I plug in 1/2. So first, let's find that. So this is asking for the tan inverse of 1/2 times 2, which is really the tan inverse of 1. So when is tangent 1? The first place that tangent is 1 is at pi over 4. So that's what I'm going to use. Okay. So now we need the derivative for tan of 2x. Again, notice that there's a function on the inside, so keep that in mind. All right, so the derivative is, for the tan inverse, if you recall, it was 1 over 1, no square root, 1 plus my function squared. And then, of course, times the derivative of whatever's inside, which is 2. So I have 2 over 1 plus, careful, 4x squared. And then that's the derivative. We're almost done, but we need the slope, which is why we found the derivative, and we need it when x is 1/2. This actually comes out quite nicely. Squaring 1/2 gives me 1/4, and 1/4 times 4 is 1, which just gives me 2 over 2, or 1 for my slope. So my equation, y minus the y value, slope, x minus the x value. If you want to simplify this, that's awesome, but you know that I'm fine with this. Okay, so you're going to have problems to work through. You do not have to derive the derivatives of the inverse like I did. I just wanted to show you where it came from, because if you ever do get stuck, you can kind of see that. I will point out a couple of things. As you're looking at it, if you're trying to remember, which one's positive and which one's negative, well, think of it like this. The derivative of cos, regular cos, is a negative sign. That's where part of that comes from. We saw that when we did the derivative. So that's why that one's negative. The derivative of regular sine is just positive cos. That's why that one stayed positive. And then you can use your own devices to remember the tan and the secant. But you will need to use both, and we will not be doing the cotan and the cotan and the cosecant. So you could derive those, though. They're not that hard if you can do the ones that we just did. So good luck on your problem sets. And again, if you need to watch some of those again, feel free to, and we'll talk more about this when I see you.